Welcome back to the Introduction to MEMS series. My name is Chang Liu. This is the second part. Uh, we're going to discuss why the semiconductor material is such an important discovery and such an important engineering material. This is the outline of the series. Right now we're on part two, why semiconductor is important. The semiconductor is a very interesting material. Uh, it is made by melting sand, one of the most abundant material on Earth. And we purify the melt to form silicon and then form large crystal silicon wafers. The material's name may be misleading, but the important thing is that a semiconductor can be doped. You can add impurities to it to form p-type or n-type. And when the p-type and n-type merge at the interface, we form what's called a p-n junction. And the conductance of the p-n junction can change. And the semiconductor is made of non-metal materials. It's not metal. In such material, the electrons are harnessed by the nucleus and can be freed when you apply heat or electric energy. One of the most important skills of a semiconductor material is to form a electrically controllable switch. The switch is called a transistor, which is short for transresistor, meaning it's a resistance whose value can be changed, can be transformed. And this is called a MOS transistor. MOS stands for metal oxide semiconductor. The structure of this device looks like this. You have metal, oxide, and semiconductor substrate. The semiconductor has a region called a channel. The gate metal is used to control the conductance of this channel. The current runs between the source and the drain, and this is formed by doping. The MOS transistor is one of the most important switching devices. But beyond that, people find out the ability to put many of the MOS transistors on the same substrate. This is called coplanar integration. So on the same substrate, you can interconnect the gate metal and the source and drain, and you can form different kind of inverters, different logics, different memory devices, and so on. So this is a very versatile building block. You may have heard that transistors and computers becomes heated when there's a lot of computation. The reason that they become heated is because the source and drain region does have finite resistance. So when you pass a lot of current back and forth, they start to have ohmic heating. This is a cross-section of a single MOS transistor. This is a metal region. The oxide is very thin, and it separates the source and drain. The source and drain, it's separated to the nearby devices through a silicon oxide trench. So this MOS device is one of the fundamental building blocks. It's one of the switching devices that's only available in the electrical domain. It doesn't exist in the mechanical domain. Now, one can make those MOS devices and package each individual transistor into a device. This is how things used to be done. So each one of these canisters, you can see, have three legs: and source, drain, and gate. And you can put them together on a circuit board to form a circuitry. Uh, Before this MOS transistor, people were using vacuum electronics as a switching device. So you can also form what's called a discrete electronics. The opposite of discrete electronics is integrated electronics. So the way that VLSI, very large scale integrated circuits, are made is by interconnecting the transistors. For example, this is a circuit diagram of two transistors joining on one gate. This is the topological interpretation. This is called a circuit layout. So you have the gate and two transistors, source and drain and source. And this basically is how the layout is done to make this circuit diagram on a silicon substrate. Here is a picture of modern electronics. You can see as the line width becomes smaller and smaller, you can pack more and more transistors into the same space, into the same real estate of the wafer. Modern chips can contain billions or tens of billions of transistors on one design. And this is a layout. And this is a demo of Intel's Pentium. In a Pentium, this is called a monolithic integration, where all the transistors are made on the same substrate surface and with different regions. And in 2025, Intel no longer relies on this monolithic integration. It also uses chiplet integration, as we'll discuss later. But the number of transistors on a chip like this can reach 1 billion or more. In 2000, Jack Kilby finally won a Nobel Prize in physics for the invention of the planar integration of VSI. And unfortunately, the founders of Intel couldn't share this prize with him at that point. But this at least showcase how important the technology is for humans. This is a schematic diagram of different layers of circuits. And because the MOS transistors are so densely packed, one needs to fan out the connections through many layers of metal interconnects. And you can see a cross-sectional view of copper gates and with many, many layers of interconnects. And the silicon is only at the very bottom of this. This is the only layer where there is semiconductor material. In 2025, people are talking about AI chips, and AI chips, the performance is increasing. This just shows that even after the Moore's law, the continuation of improvement is still there. And you can argue that it's probably going to be even more than during the Moore's law. And many chips are packaged together in a system. It's called a system on chip. And this is an example of a Google GPU, the Google TPU, Tensor Processing Unit, which is innovation beyond the graphic GPU of NVIDIA. So in the Tensor Processing Unit, you have many cores and memories, and they also can be interconnected together to form clusters.